Okay, in this video we're going to talk about the ambiguous case. So that's the situation where we have a triangle and we're not sure exactly what to do with the triangle because of the information given to us. The ambiguous case occurs when we have angle side side or side side angle if you're proper. Okay, angle side side, which obviously is a very funny acronym, is when we have, for example, and you'll see an example of this soon, we have something like this. We have like this is 30 degrees, this is 4, and this is 5. Okay, so this is an angle side side triangle. And we have different things that could happen here. This particular one I just drew, there's only one thing that can happen just because of the way I drew it. But we have to consider that there could be weird things afoot. So first thing you should think of when you see a triangle and you're only given one angle is this an angle side side triangle? So if you're given, for example, if I was in this problem given this one, there's no issues whatsoever. Law of Cosines will find that missing side and you'll be good to go. However, right, that's side, because that's side angle side if we read it clockwise. If we're reading it angle side side, now we have a problem potentially, so we have to consider that. Now what can happen? Well, 4 different things could be the case here. We could have a single oblique triangle. This one, I believe, if I'm not mistaken, is a single oblique triangle. Okay, we could have a right triangle. That's a really nice situation. We could have 2 oblique triangles, or we could have no triangle. And let's look at why each of those things might occur. Okay, so this laid out as simply as I can. If you compare the side lengths that are given to you, you can kind of figure all of this out. So if A was greater than B, so in that previous example, that side length of 5 was greater than the side length of 4, we're going to end up with a single oblique triangle, and it's obtuse. Okay. We also have the possibility that the side length B is exactly equal to B sine of alpha. Well, why is this significant? Well, right angle trig, right? If we had a right triangle and we wanted to find this side length, right, and this was known. Sorry, let's make x the thing we want to know. And this was known and this was known. Like say it's 30 degrees, for example, we would say the sine of 30 degrees is equal to x divided by a, and since we want to know x is equal to a sine 30, a times the sine of 30 degrees. Right, so if that happens to be the exact size, then we have a single right triangle. That's a really convenient situation. It's kind of a pain to figure that out, but that's the case. Right, and this is the danger here. These next 2 things is we could potentially have 2 triangles. Now, what does that mean that we could have 2 triangles? Well, if you think about it, we were given side length B and side length A. And so if we have a situation where we didn't know the angle C, which we don't in this situation, and we had pretend there was like there's a hinge right here, and this known distance of A was allowed to hinge about that point C, well, we could have this triangle over here, and then of course we would have 2 different side lengths for C, and that's going to be the case. I'll come back to that in a second. And then the last situation is when A just is not long enough to connect to C at all. So we wouldn't have enough, the side length of C is not enough to, side length of A in this drawing is not enough to constitute a triangle. Okay, going back to the 2 obtuse triangle things, a very important realization to make here is that if I have this angle, let's call this angle beta B sub 1, okay? And then I look at this angle over here, which is B sub 2. What you need to notice is that we have right here, oh sorry, that's not B sub 2, I'm sorry. B sub 2 is for this other triangle, right? What you need to notice is that what we'll have in this triangle, which I'll draw here in red, and this is a isosceles triangle, because this angle and this angle are the same. And then, since this is a straight line, these 2 angles need to be supplementary. So B1 and B2 are supplementary, or are always supplementary if there's 2 different angles. Supplementary, okay? That's really important because it's the foundation behind one of the ways we can tackle these kinds of problems. Okay, I'm going to come back to this slide and draw some more stuff on it after we talk about some other things. But for now, these are the 4 different scenarios. So how do you go about doing this? Well, you can use the law of sines, and I don't recommend this at all, but this is how you can do it. Okay, first of all, we recognize this is angle side side. It's an ash triangle. We need to consider that this is an ambiguous case, so figure out what the possibilities are. So what we're going to do is just use the law of sines, because you can set up a ratio here. You can totally do that, right? We have, for example, well, not for example, let's say we want to find beta. That would be the only thing we'd be able to find based on the information we have. So the sine of beta is to the side length of 16, as the sine of 30 degrees is to the side length of 10. So if we go through the process that we've done before and solve for angle beta, the inverse sine of 16 times the sine of 30 degrees divided by 10 is going to give me some angle, right? Now, the recognition here is, what is that angle? First of all, if that angle is 90 degrees, obviously we have a right triangle. If this just doesn't work, meaning like this is an inverse trig function, right? So what are we allowed to plug in right here? Well, we're only allowed to plug in values between -1 and 1. Like this, that's what it'll work out to be. If we're outside of that range, well, then we have a situation where we don't have a triangle. And then the final possibility, of course, is when we is what we're going to consider next. So when we plug this in, let's see what we get. I actually don't know. Did I type this in? No, I didn't. Okay, so we're going to get the inverse sine of 16 times the sine of 30 degrees divided by 10. Okay, and so we get 53.13 comes out of this. Okay, now 53.13 comes out. However, from the previous slide, we know that if there is a second case, that angle, like we'll call this B1, beta sub 1. We know that beta sub 2 is equal to 180 minus beta sub 1. That's the other possibility. So what does that mean? Well, for this particular case, 180 minus that answer, it gives us 127. Oops, sorry, 126.8, 126.9, or whatever. Let's say that's 0.1, that's 0.9. Okay. Now, what you have to think about here is, all right, we have the possibility where it's kind of as drawn. This would be 53.1 degrees, or we could have this over here where that is 126.9 degrees. If in either of these cases the triangle isn't possible, then we only have one answer. Well, what does that mean? Well, we know this angle of 30 degrees. And we're saying, all right, this is 53.1. So it's possible that this angle is the remaining part of 180. Meaning, essentially, that 30 plus, well, let's just draw this. Let's say this was angle alpha, right? It means that angle alpha plus angle beta is less than 180 degrees. So that's possible for there to be an angle gamma. Now, why would that, how would that ever not be the case? Well, if we had, for example, on this triangle, right, this beta 2 is also is less than 180 degrees. If I add 126.9 plus 30, it's less than 180. If I had got an angle here, like let's say 155 degrees for my supplementary angle beta, then I would have 30 plus 155 is 185. That's already too many degrees for there to be an angle gamma. So that triangle, that possibility would not exist anymore. So it's kind of convenient in a way to do law of sines this way. There's just kind of all these little analyses you have to do. So in any case, what do we have to do to solve this problem in the end? Well, there are two triangles. We've shown that because both of these things are true. So what is angle beta? Well, angle beta could be 53.1 degrees, or it could be 126.9 degrees. Okay. We also are going to need to find side length C and angle gamma. Well, we need angle gamma, right? Okay. This one's really easy to get because we have the 30, we have our angle alpha, and now we have our new angle beta. So how would we do that? 30 plus 53.1, right? 180 minus that. That gives us our possible gamma 1, essentially, 96.9. Okay, and then the other one would be 126.9 minus the plus 30, and then 180 minus that. Okay, that gives us our 23.1. So that's fine, but we're still missing here now our possible our side length C. And the way we do that is just by doing the law of sines again. That's totally fine. Now that we have these two different possible angles for gamma, we can set this up to find side length C easy. Okay, so like for example, right, C is to the sine of gamma as let's use the 10 is to the sine of 30 degrees. Keep it simple that way. So C is equal to 10 times the sine of this first gamma, 96.9, divided by sine of 30. So that's like C1, right? And then C2 would be 10 times the sine of our other gamma, 23.1 degrees, divided by the sine of 30. So what are those? 10 times the sine of 96.6 divided by the sine of 30. So that's going to be 19.87. If we're this one, we would expect side length C to be much smaller than in this other triangle. So what's that going to be? 10 times the sine of 23.1 sorry, I forgot the parentheses, divided by sine of 30, which is 1/2 obviously. Okay, so we get 7.85. So there we go. We've solved this triangle, right? There were two different triangles here. It's kind of the pain in the butt. It totally is. Let's look at a different way we can do this. That's pretty interesting, okay? It's by using the law of cosines. Remember, the law of cosines is we're just going to use that standard form where the angle we're given is alpha. We're just calling it alpha. Okay, and the other two side lengths we have are going to be A and B. So we're going to be using this form of the law of cosines to solve for C. If we solve this equation for C, you're going to find that we run into the quadratic formula. Okay, think about that. We'll just move essentially we're going to move everything to one side. A squared and B squared are just going to be numbers, and then we're going to have a term essentially where it's going to be let me write this. We'll basically have 0 is equal to C squared minus 2bc times the cosine of alpha and plus some number. Okay, this number is whatever b squared minus a squared is. This is like b squared minus a squared. Right, so this is just a number. This is a coefficient with a c, so 2b times the cosine of alpha is a coefficient, and then c squared. If there's a quadratic and we have the quadratic formula, okay, well, what are the possibilities with the quadratic formula? Okay, and we'll also think about what the quadratic formula represents. So if the quadratic formula gives us two positive values for C, we're going to have two triangles like we just had in the previous example. Okay, if the quadratic formula gives me one positive value for C and one negative value for C, we throw out the negative value and we just use the positive value. That means there's just one oblique triangle. If the quadratic formula gives us no real solutions, meaning they're imaginary numbers or they're complex numbers with non-zero imaginary parts, then we don't have a triangle. That side length B wouldn't have the side length C. Just it won't work. You can't have one because B doesn't connect to it. Okay, and now let's look at the other. There's also another possibility here I didn't write, and it's when you have two of the same answer that comes out of the quadratic formula. So like one answer is essentially two of the same because quadratic formula gives you two answers. Well, what does that mean kind of like conceptually? Think about what a quadratic is and what the solutions to a quadratic represent. So here is, I'm going to draw these little coordinate planes and we'll just sketch in these graphs that represent what's happening when we solve the quadratic formula for these things. So in the case where we have one triangle, we have this possibility for the solutions to the quadratic, remember, are where they cross the x-axis. So one positive, that's the answer, okay? We also have over here, we have the situation where we have two of the same answer, meaning it touches. This is a situation where the vertex of the parabola is right there on the x-axis. That's a right triangle. Okay, what's this one? What's the one where we have 2? It's when we have something like this, right? It crosses the x-axis twice on the positive side. So we have 2 different values for C. Both of them are legit. Okay, and then the last one is when we just have a parabola that's out, it's floating, meaning there is no real solution. There are non-real solutions, yes, but we have to have real solutions because we're talking about a triangle. The value for C needs to be a real number. It also needs to be positive, which is why this negative solution over here doesn't work. So that's what's happening when we do this other method using the law of cosines, which, to be honest, is kind of preferable. So let's go and look at that. We're going to solve this one here. Oh, actually, really quick, we already see that this is greater than this, so this is just a single triangle. So that's fine. Actually, I mean, we could double check to make sure that, no, this is definitely just a single triangle. So we can solve this one. We can actually just use a law of sines here. We don't have to use a law of cosines at all. So if we wanted to find this angle, right, we would say the sine of 40 degrees is the side length 3, as the sine of angle alpha is to 2. And so we solve this for alpha. It's going to be the inverse sine of 2 times the sine of 40 degrees divided by 3. What's that? I don't know. The inverse sine of 2 times the sine of 40 degrees divided by 3 is 25 degrees, 25.37 degrees, 25.37. Okay, and we can find beta. We'll say that this is beta, okay, up here. That's just going to be 180 minus 40 minus this 25.37. So what's that? I don't know. Plus 40, 180 minus that. Okay, so that means beta is 114.6. What was it? 6 is going to be 6.3 because I'm just making it round numbers. And then we can use the law of sines again to find this side length over here. Let's call that side length B. So B is to the sine of 114.63 as 3 is to the sine of 40. So B would be 3 times the sine of 114.63 divided by the sine of 40. Now again, we're not going to use 114.63. We're going to use the value that's in our calculator, which was this thing, right? So 3 sine of that answer divided by the sine of 40. Okay, 4.24. So B is 4.24. So this is a single triangle, and we have that side length and these two angles. Now, what about when we have the bad situation? Okay, so this was a problem where we're primed for having a bad situation. We have angle side, so it's ambiguous, and this side length C is less than this side length B. We could go as far as to say, all right, is this going to be a right triangle here? Well, is 6 equal to the 8 times the sine of 35 degrees? Like, I'll tell you right away, it's not. Okay, so this is not going to be a right triangle, so that sucks. So what we're going to do is use the law of cosines here. So remember what we have. A squared is equal to b squared plus c squared minus 2bc times the cosine of angle alpha. Okay, so this is alpha, right? This is A, this is B. Now we're going to find C using this. So we're going to solve this for C. We're going to move everything to the right side. So 0 is equal to c squared plus b squared minus a squared minus 2bc times the cosine of alpha. Plug some numbers in here. C squared plus 8 squared minus 6 squared minus 2 times 8 times c times the cosine of 35 degrees. Let's rearrange a few things here. So that's going to be c squared minus 16 times the cosine, I'm going to put this all in parentheses. 16 times the cosine of 35 degrees times c, and then 64 minus 36 is some kind of number. I believe it's 28, right? So plus 28. Is that right? 64 plus 28. Sorry, 84 minus 36. That sounds right. Hopefully that's right. I can't do the math in my head right now, so we're hoping it's right. All right, so what do? Well, plug this into the quadratic formula. Literally, like, so we're going to plug this into the quadratic formula, which is x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. Now, it's confusing here because c isn't c, right? It's just we're pretending it's x, right? So what is, so a, it would be 1 in this situation. B would be negative 16 times the cosine of 35 degrees, and c would be 28. So we're going to plug these values into the quadratic formula and see what comes out. I don't think I have the quadratic formula in here. I don't, so we're just going to type it in. We can even use our little fraction thing here, which makes it nice. So we have negative 16. So I'll just say it's, you know what, actually, you know what we can do? This will be cool, watch. We can say 1 and restore that as a. We can say negative 16 times the cosine of 35 degrees. And we're going to store that as b. And then we're going to say 28, and we're going to store that as c. Okay, now what we can do is go and type in the quadratic formula here, right? Negative b, negative alpha b plus the square root of alpha b squared minus 4 alpha a alpha c. Nope. Yeah, we're not under the thing anymore either, huh? We gotta fix that. Sorry, it's hard to navigate on this computer, on this calculator. So let's fix that. So minus 4 alpha a alpha c. Okay, delete. Okay, now divided by 2 alpha a. Okay, so one of the answers that comes out is c. C could be, and this is side length c, not c from the quadratic formula. It could be 10.41. And the other one that could come out is, of course, if we have a minus there instead of a plus. So let's do that. A minus instead of a plus. Right here. We have 2.68. 2.69. 2.69 that comes. So we have C1 and C2 here. So let's write down what we've got. So we have side length C could be two different things. It could be 10.41 or it could be 2.69. Okay, so we have in this, as drawn, it would be 10.41. The other possibility though is like this triangle, right? Or those are the same. These are the same. And we have this other angle here. So now what we need to do is find, and this is going to be beta over here. This will be beta 1. This will be beta 2. Beta 1 equal to that. And beta 2 will be over here. So what do we do here? Well, we can use the law of sines now. Okay, and since we know it's established that it's, we can do this a couple different ways, to be honest. We can use the law of sines with these new c values we found to get the two different values for gamma, and then get supplements for beta. That's fine too, supplementary angles for beta. So actually let's do it that way, because you can use the law of sines here just like we did in the previous problem. But if we want to find gamma now, right, this is gamma. No, that's not how you write gamma. That's gamma. Gamma would equal, let's set it up, the sine of gamma divided by divided by C1, which we have, would be the same as the sine of 35 degrees divided by 6. Right, so we have a situation where gamma 1 would be the inverse sine of C1 times the sine of 35 degrees divided by 6, and gamma 2 would be the inverse sine of C2 times the sine of 35 degrees divided by 6. And we have C1 and C2. We'll just use these rounded values for now because I don't have them saved. I don't think I have them saved nicely in the calculator. Well, we can do that. We can actually use the exact values. So inverse sine of this value times the sine of 35 degrees divided by 6 gives us one possible value for gamma of 14.8, and that's when we had the small one. So 14.9 degrees. The other one, let's just go up and get this value. Okay, so we want inverse sine of that value times the sine of 35 degrees divided by 6 gives us our other possible angle of 84.9 degrees. So 84 point, sorry, I wrote that backwards, sorry. So this was our 84.9 and this was our 14.9. Okay. Right? Yeah, 84.9, 14.9. Now, what is beta? Well, beta we can get by just doing subtraction, right? We know that 180, so beta 1 would be equal to 180 minus 35 minus 84.9. So add 35 to that, subtract that sum from 180, and we'll get 60.1. Okay. And then the other one would be, now these obviously don't quite add up because, well, it does, right? 60.1 and 84.9, that'll work out. And then the last one, these are degrees. The last one we would do 180 minus 35 minus this 84.9, right? And we get, oh wait, we did that wrong. Sorry, 180 minus 35 minus the other one, which was our 10.4. We get 134.6 degrees. Wait, well, that's the wrong thing too. Sorry, I used a side length there. Okay, we're gonna do this one more time. We're gonna get it right. I promise. 180 minus 35 minus the angle value that we were messing with before, which was this 14.8. Okay, there we go. So 130.1 because the other possibility for beta. Right, and so that is how you can use the law of cosines. I know that process seemed maybe a little bit more cumbersome, but the thing is it works every single time, and depending on what comes out of the quadratic formula, you'll know what's going on. We'll get more practice on this later, but that's got to be the end of this video because it's already super long. Apologize for that, but hopefully this has given you some clarity about the ambiguous case.